Edexcel Master, exam made clear.
Ever stop and think about why you can grab a plastic-coated wire without a problem, but you'd never touch the copper inside? It all comes down to a really simple question. Why do some materials let electricity just flow right through, while others stop it completely cold? Well, today we're going to explore that entire spectrum, from what are basically electrical superhighways all the way to complete roadblocks. And this isn't some abstract science stuff. It's a principle you interact with constantly. The whole reason your phone charger's plastic case is safe to touch, or why a pot handle doesn't burn your hand, it all comes down to the behavior of one tiny but incredibly important particle. So let's meet the hero of our story, the free electron. You can think of these as the tiny little couriers of electrical energy. The entire difference between a material that zaps you and one that doesn't, it really just boils down to one thing. How many of these free electrons are available to get up and move? Okay, so let's start at one end of our spectrum. I want you to imagine a massive 20-lane superhighway. There's no speed limit, no traffic, nothing but open road.
Well, that's exactly what a conductor looks like to an electron. What makes a conductor so special is that it's just teeming with these free electrons. They aren't tied down to any one atom. Instead, they form this huge collective sea of charge that's just ready and waiting to flow the second you give it a little push with some voltage.
And when I say massive, I am not kidding. Just look at that number. That's a 1 with 23 zeros after it. In a conductor, a tiny space, like the size of a sugar cube, is packed with roughly 100,000 billion free electrons. It's an unbelievable crowd just waiting for a reason to move. And that movement, well, that's what we call electricity. And this is exactly why the wiring in your house is made of copper, and why really high-end electronics sometimes use silver. These materials are just the perfect superhighways for getting electrical energy from point A to point B with almost zero hassle.
All right, now let's do a complete 180 and jump to the other end of the spectrum. If conductors are those wide-open superhighways, then insulators are just giant, impenetrable brick walls. They are the ultimate roadblocks of the electrical world.
See, in an insulator, pretty much every single electron is on lockdown, tightly bound to its home atom. They are not free to wander around. So if you apply a voltage, there's just nobody available to carry the charge and create a current. The flow is stopped, completely dead in its tracks. And here's where it gets really wild. Remember that mind-boggling number for conductors, that 100,000 billion? Well, in that exact same sugar cube-sized space, a good insulator might have maybe just one free electron. We're talking about going from a number so big you can't even imagine it, all the way down to 1. That colossal difference is everything. And this is why everyday objects are designed the way they are. That rubber or plastic coating on a wire, it exists for one reason, to be a barrier. It keeps that electrical superhighway contained, making sure the energy goes where it's supposed to, and maybe more importantly, keeping you safe. Okay, so we've seen the highway and the roadblock, but you know what? The most revolutionary materials are actually the ones that are neither. This is where the real magic happens. Let's move to the middle of our spectrum, because this is where we get the technology that basically defines our modern world. So here's the crucial thing. Semiconductors are kind of like the Goldilocks material. They're not great conductors, but they're not perfect insulators either. They sit right in that sweet spot in the middle, and this is the key. We can precisely control how conductive they are. That control, that's their superpower. And their number of free electrons sits perfectly between our two extremes. It's way less than a conductor, but it's vastly more than an insulator. And this gives them this unique starting point, a state of being kind of partially on, which we can then tweak and manipulate. And the most famous of these, of course, is silicon. This one element, this wonder of the middle path, is the literal foundation of pretty much every computer chip, every smartphone, every digital device you own. Its ability to be switched on and off is the basis for all digital logic. It's the whole game. Okay, so we've got our three main categories: conductors, insulators, and these amazing semiconductors. But why is this simple classification so unbelievably important? Let's bring it all home. This table really just lays it all out so clearly. You can see the absolutely staggering difference in the density of free electrons. We're talking orders of magnitude here. It's this one physical property that decides if a material is going to be a wire, a switch, or a safety shield. Every single piece of electronics you own is a carefully designed combination of these three types of materials. We use conductors, the highways, to move electricity around. We use insulators, the roadblocks, to direct it and keep us safe. And we use semiconductors to control that flow, and that's how we process information. And that really is the key takeaway here. Our ability to master that middle ground, to turn a chunk of silicon from a pretty lousy conductor into a precise electrical switch that can be flipped millions of times a second, that's what separates a simple light bulb from a supercomputer.
And that, of course, leaves us with a really fascinating question. For the last 70 years or so, silicon has been king. But what's next? What new material with its own unique electrical properties is just waiting out there to be discovered? Something that could spark the next technological revolution. It's something to think about. Thanks for diving into this with me.